in the universe are governed by 4 laws. These are Maxwell's 4 laws of electromagnetism. Just a single charged particle creates an electric field everywhere throughout the entire universe. Suppose we enclose the charged particle inside an object. The number of electric field lines leaving the object is determined by the amount of charge inside. Electric fields exert a force on all charged particles. The strength of the electric field depends on the number of electric field lines. Field lines extend to infinity in all directions. The electric field is strongest near the charged particle, because this is where the greatest number of electric field lines are close together. Maxwell's first law is that the number of electric field lines leaving an object is determined only by the amount of charge inside. Charges outside the object bend the lines, but do not change the number of lines that exit the object. The only way to increase the number of lines leaving the object is by increasing the amount of charge inside. Since the amount of charge inside the object has now doubled, there are now twice as many electric field lines leaving the object, and the electric field is twice as strong. The number of electric field lines leaving the object does not depend on the object's shape or size. Maxwell's first law says that so long as the amount of charge inside the object does not change, the number of electric field lines leaving the object will stay constant. The direction of the lines indicates the direction of the electric fields. Electric fields have an opposite effect on negative particles than they do on positive particles. Positive particles feel a force in the same direction as the electric field. Negative particles feel a force in the opposite direction of the electric field. Particles with the same charge repel one another. Particles with opposite charges attract one another. Because positive particles cause electric fields to point away from the particle. Negative particles cause electric fields to point towards the particle. This means that electric field lines go out of positive particles. And electric field lines go into negative particles. Negative charges cancel out positive charges. The number of electric field lines exiting this object is exactly equal to the number of electric field lines entering the object. The net number of electric field lines leaving the object is 0, and the net charge inside the object is also 0. Magnetic fields are very different from electric fields. Maxwell's second law says that the number of magnetic field lines leaving an object is always 0. No matter an object's shape or size, the number of magnetic field lines entering an object will always be exactly equal to the number of magnetic field lines exiting. This is true regardless of whether or not there are charges inside. Magnetic fields are created by moving charged particles. As was the case with electric fields, how close together the magnetic field lines are to one another indicates the strength of the magnetic field. Also, as was the case with electric fields, the direction of the magnetic field lines indicates the direction of the magnetic fields. Maxwell's third law states that the strength of a magnetic field around a loop depends on the amount of charge passing through the loop each second. If we increase the amount of charge passing through the loop, the strength of the magnetic field increases. Negative particles flowing through a loop create a magnetic field in the opposite direction. All moving charged particles create magnetic fields. Magnetic fields exert a force on all moving charged particles. Negative particles experience a force in the opposite direction of positive particles. electric fields, particles feel a force parallel to the direction of the electric field. In the case of magnetic fields, particles feel a force in a direction that is 90 degrees to the magnetic field. And 90 degrees to the direction of motion. There is a rule for using your right hand to remember the direction in which a moving positively charged particle will create a magnetic field. There is another rule for using your right hand to remember the direction in which a magnetic field will exert a force on a moving positively charged particle. The result is that particles with the same charge moving in the same direction result in a magnetic force attracting them together. The opposite is true for particles with the same charge moving in opposite directions. Particles with the same charge moving in opposite directions result in a magnetic force pushing them apart. A rotating charged particle can be thought of as a loop of charged particles. This creates a magnetic field that enters on one side and exits on the other side. Let's call one side the South Pole and call the other side the North Pole. A magnet is a material which has many of its negatively charged particles spinning in the same direction. Every rotating charged particle is a miniature magnet, and every magnet can be thought of as a rotating loop of charged particles. Suppose we have two magnets aligned in the same direction. In this case, since we have particles with the same charge moving in the same direction, there will be a magnetic force attracting them together. Now suppose that we have two magnets aligned in opposite directions. In this case, since we have particles with the same charge moving in opposite directions, there will be a magnetic force pushing them apart. Opposite poles attract attract one another. Similar poles repel one another. Now suppose that we have two magnets aligned in random directions. Particles with the same charge moving in the same direction will have a magnetic force pulling them together. This will cause the two magnets to align in the same direction, resulting in an attractive force. A material doesn't have to be a magnet to be a magnetic material. Magnetic materials have rotating charged particles that can be affected by magnets. Normally, these rotations are in random direction. In the presence of a magnet, the rotating particles will align in the same direction. This is what causes magnets to attract certain objects. Instead of using a magnet, we can also use a coil of wire. Charged particles moving through a coil create the same forces that magnets do. The strength of the force depends on the strength of the magnetic field. The strength of the magnetic field around a loop depends on the amount of charge passing through the loop each second. We can increase the number of charged particles passing through the loop each second by increasing the number of turns in the coil. The number of particles flowing through the loop each second is the number of particles flowing through the wire each second multiplied by the number of turns. More turns in the coil results in a stronger field and in a stronger electromagnet. We can also make the coil far stronger by inserting a magnetic material inside. The magnetic force from the coil will cause the rotating charged particles in the material to align in the same direction. With the charged particles aligned in the same direction, the material behaves like a magnet. greatly strengthening the magnetic field created by the coil. For certain materials, the rotation of the charged particles will stay aligned even after the coil is removed.